Hello everybody. I am Prashant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In the last class, we have completed the Unit 1, where we have studied fundamentals of AC machine windings, its physical arrangements of windings in stator and cylindrical rotors, slots for windings, different say coil, singleton coil, its portions, active portions, overhang, full pitch coil, concentrated windings, then distributed windings, and distributed windings means single layer winding, double layer winding, and how these windings are arranged in the slots. Not only that, we have studied say air gap magnetic force distributions with different current, fixed currents, and say alternating currents. Then we have say learn about winding factors, which is coil pitch factors and distribution factors, and that's all we have learned. Now today we'll start a new unit 2. So unit 2 will mainly deals with pulsating and revolving magnetic fields. So this unit contains constant magnetic field, pulsating magnetic field, alternating current in windings with spatial displacement, magnetic field produced by a single winding, fixed current, and alternating current pulsating fields produced by spatially displaced windings, windings spatially shifted by 90 degrees, addition of pulsating magnetic fields, three windings spatially shifted by 120 degrees, carrying three-phase balance currents, and revolving magnetic fields, etc. So basically, this chapter deals with the different types of magnetic fields which is created due to fixed current or alternating current, or due to single winding, or due to distributed winding, and say spatial displacement between the windings. If it is two windings, then if it is a 90 degree, or if it is a three winding, which is 120 degrees, and provided with a balanced three-phase supply. Then this windings actually basically this field, magnetic field, which is being created due to these arrangements. So what is its nature? What is constant magnetic field? What is pulsating magnetic field? And what is revolving magnetic field? And what is its importance in the study of electrical machines? So to start with, so we'll discuss first with constant magnetic field. So as the name suggests, a constant magnetic field means the amplitude or the magnitude of the magnetic field is always remains same. So it will not move. It will with time, or it will not change space, etc. So when a magnetic field is increasing or decreasing, the force it exerts on electrons is changing. Definitely because of its changing nature, due to its increasing nature or decreasing nature. The force actually it exerts on any charged body definitely change. Now, forces on electrons are unbalanced. Basically, it is due to this changing nature. So point to point, the forces will not remain same. And as a result, so due to this unbalanced force or imbalanced force, so torque will be developed due to force, and this charge particle will move. But when this magnetic field becomes constant, the electrons reach a new point of balance and stop moving. Okay, so this is a very nature of a constant magnetic field. No charge particles will move this field, and it will not say feel any force on it. So as a result, it will not move. Now, what is then pulsating field? Pulsating field due to alternating current in windings with spatial displacement, if we think. So pulsating field means it pulsating means it's pulsate. Pulsate means its magnitude will change with time, but it will not change its position. Okay, so from it stands still at one point. In this point, it will go on increasing, and then it will decrease, come to the say starting position, and then it will decrease and in the other direction, and it will move to its maximum value in this direction, and then it will follow. So it will at one point it will just increasing and decreasing. Then so this is a pulsate. Actually, it will not moving. So that's why it's this very nature of magnetic field is known as pulsating field. So it is created by pulsating current, definitely. Maybe it's alternating current. Now, actually, in electrical machines, so if we supply in a single winding, that is a single phase winding, by a single phase AC voltage, then resulting magnetic field coming out of the teeth of the core will be pulsating. Basically, you know, we have seen in the our first say unit or module 1 or unit 1, where we have seen the windings are placed in the slots of the core, and so in between two slots there is teeth. So this resulting magnetic field coming out of the teeth of the core, so will be pulsating. That is of alternating nature. So as AC current has a sinusoidal waveform, hence the pulsating magnetic field created by this alternating current will also be of sinusoidal shape. Then these sinusoidal shapes can be seen. How will say detect this shape is sinusoidal? So if we use CRO, then we can find this with this CRO we can find the shape of this magnetic field. The magnetic field of this very nature of this magnetic field will be pulsating because as I told you, the magnitude of the magnetic field, that is the flux density, changes its magnitude with time at frequency of supply voltage. And you know, this pulsating wave is stationary in nature. That is, its phase does not change with change in position or point of in measurement of flux density above the defined teeth and slots. So this can be observed when and in electrical machines with open air gaps, such as linear induction motor or rotor revolved removed induction machine, that is in the hollow stator only, is available. Actually, these are available in the lab. So that's about the pulsating magnetic field due to alternating current in windings with spatial displacement. Now we'll talk about the pulsating fields produced by windings with spatially shifted by 90 degrees, and how these pulsating magnetic fields can be added up. Now, with this, suppose the magnetic field produced by a single winding, it has fixed current and alternating current. It is pulsating field, and is produced by spatially displaced winding. The windings are shifted by 90 degrees. Now consider two windings. Let's say this is shown here. There are two windings A and B, and you see they're displaced, so displaced they can produce magnetic fields which are 90 degrees apart in space. That is shown here. Okay, this is the flux of due to the A winding, and this is due to B winding, and you was finding that these are 90 degrees apart. Okay, now these windings produce magnetic field in magnitude, and since they are 90 degrees apart in time, so this can be written as this phi A equal to phi m sin omega t, and phi b equal to phi m sin omega t plus 90 degree. Okay, so this is the flux, and it is its angular velocity. So this is production of uniform magnetic field. Now the waveform of these fields is shown here. This is the waveform. Okay. Now the resultant of these two fields is of course rotating fields of constant magnitude of phi m, and this rotating magnetic field may be represented by a phasor of constant magnitude of phi m, and that is shown here. This is the phasor, shown the constant magnitude, and phasor describes a circle. See, this phasor is describing a circle, and in each revolution, this phasor of course describe a circle, and each revolution of the phasor correspond to one cycle of the supply frequency. Now suppose that the two windings A and B are displaced 90 degree in space, but produce fields that are either not equal or not 90 degree apart in time. This is on. So this is not 90 degree apart, or not they are equal. You are finding these magnitudes are not equal. So the resultant of these two fields is again a rotating field, of course, because if you add up these two pulsating fields, which are not 90 degree actual 90 degree apart or in space or in time, so their magnitudes will be not same, and they still their resultant will say resultant will be of this field again a rotating field, but this field is variable in magnitude throughout each revolution. And similarly, the resultant of the two fields displaced both in time and space by some angle other than 90 degree is a non-uniform rotating field. Non-uniform magnetic field produces a non-uniform torque, and which makes the application operation of the say motor or noisy. And the other effect of non-uniform field is upon the starting torque. Definitely, it will hamper the starting torque. And motor having a more uniform rotating field has a larger starting torque in comparison to a motor of the same rating having a non-uniform rotating magnetic field. So that's the very peculiar thing. So if the spatial displacement between the windings are not exactly 90 degree, or if they are not in time phase of equal say 90 degree, or then the magnitude and positions of their phasors will be different. So we have discussed pulsating field produced by windings spatially shifted by 90 degrees and uh, addition of pulsating magnetic fields. And what we have seen uh, in this discussion that so this type of actually what is the need of necessity of studying this uh, pulsating magnetic field. Basically, when we will, you know, we have discussed that this type of field is produced due to single phase winding, and when we will study the single phase motors, particularly single phase induction motors. So, what is how it is being created, and why? What is its say disadvantage? So we have discussed that this type of field is, since it is a pulsating in nature, so it will not generate the sufficient torque to move the rotor of the motor, and to overcome this problem, what the technique or methodology will apply, that we'll discuss when we will study single phase induction motor. And so since this is a non-uniform magnetic field and produce a non-uniform torque, and so this motor operation will be noisy if it is the windings are spatially shifted less than 90 degree or something else. So in that case, for single phase winding or single phase motor, so how single winding can be distributed spatially almost nearly 90 degree space displacement, so that the torque can be developed, so motor can be rotate, that is rotor of the single phase motor can rotate. So that we'll study in details when we'll study single phase induction motor. So now we'll study how the rotating magnetic field is, the uniform rotating magnetic field is being created, and to create say uniform constant magnitude rotating magnetic field, we must require balanced three-phase supply to be provided in the three windings which are spatially shifted by 120 degree. And if we can arrange the three windings in spatially 120 degree shifted in such a way that the distributed windings along the periphery of the stator slots, so and if we supply three-phase balanced AC, then a revolving or rotating magnetic field will be created, which will be of constant magnitude, and and if this is being created, so this type of rotating magnetic field is used in three-phase induction motors, and it will give a easy say starting of the three-phase induction motors. So, so before that, we'll discuss all these things in details in three-phase induction motor. But how this balanced, say uniform torque is being created, or uniform magnetic field of constant magnitude is being created due to three-phase balanced supply. So we'll discuss. Now, when a balanced three-phase current flow in balanced three-phase windings, rotating magnetic field of course is produced, and all three-phase AC machines are associated with rotating magnetic field in their air gaps. Now, suppose for this we are, for an example, we take a two-pole three-phase stator winding. And let's say these three windings are displaced from each other by 120 degree along the air gap periphery, and each phase is distributed or spread over 60 degree and called the space spread say of 60 degree, and the phase windings of A, let's say they are named as A, B and C, represented by 3 full pitched coils, A phase coil A dash, B phase BB dash, and C phase of course CC dash. Now for instance, the concentrated full pitched coil A dash represent phase A winding in all respects. A current is phase A winding establishes magnetic flux directly along the magnetic axis of the coil A dash, and positive currents are assumed to be flowing as indicated by the process in coil sides A dash, B dash, and C dash. So it's shown here. So if you see, this is coil A. Okay. So this is the phase winding, A phase winding. This is the encircled cross is the current is entering in this direction, and the encircled this is the current coming out from this plane of the paper. So it is going inside the paper, and this is the current direction coming out of this paper. So that is represented here. So in this way, so that's why we have said positive currents are assumed to be flowing, so indicated by the encircled cross A dash, B dash, and C dash. So this is the current going inside the plane of the paper. This is then this is for B phase, this is for C phase, and this A, B, and C are indicating. These are the encircled dot. See, that is the direction of the current coming out of the plane of the phase paper. So of this phase. Okay, so that is shown here. So this is okay. This phase A. This is phase B, and this is your phase C. So, and this is the axis of the coil. If this is the coil, say this is the coil A for representing the phase A. So this will be this is the axis of the phase A. Similarly, this is your coil. This is your coil B or B phase winding, and this will be the axis of phase B. And similarly, this will be your phase C, or this is its axis. Okay. Now, how? So let's since if balanced current is flowing, three-phase balanced current is flowing through these 3 windings, that this is the A phase current IA. So this is its A phase current IA, and this is B phase current, which is 120 degree out of phase from phase A. So this is B phase current. So this is B phase current, and again from B phase, C phase current is another 120 degree out of phase. That means it is from A it is 240 degree, of course. Then this is your phase C. So this is the plot of the current. Now with so this is the arrangement. I told you 3-phase balanced for we have taken a 2-pole 3-phase stator winding, and but 3-phase windings are say placed or shown here, and this is the axis of these 3-phase windings. Now this diagram shows you the current distribution, or say current through among 3 phases. This is the current For A phases, this is for the current. For the B phases, which is 120 degree apart from phase with phase difference of 120 degree, and from B phase, C phase is another 120 degree phase difference. So it is I phase, C phase current, and all the currents are balanced supply. So this is IA, IB, and IC. Now, how we can plot say magnetic flux of this balanced three-phase current. Let us suppose at instant 1, this is instant 1. What is the current in phase A, phase B, and phase C? What we are finding? This is phase A. At instant, this phase A current is maximum. So, and it is positive. Okay, so if we represent phase A current is IA, so IA should be equal to its maximum value IM, and this is positive. And that is the conditions of phase B and phase C. You see, this is phase B. At this instant, phase B is in the negative directions. It is of half of its maximum value, and it is phase C. Phase C is again also of negative of half of its maximum value. So it is we are finding that IB equal to IC equal to minus IM by 2. Now what is happening at instant 2? So this is instant 2. So we are finding at instant 2 IA is again positive and IB becoming positive, but IA and IB are equal in magnitude and they are half of their maximum value. So this is IM by 2. But what is happening with IC? This IC is in the negative directions and IC is its maximum value. This is of minus IM. Okay. Now, what is its positions at instant 3? So, see, at instant 3, it is see, this is IA and IC. Both are negative, and it is yes, half of its maximum value. So IA equal to minus IM by 2 and IC equal to minus IM by 2. But see, B is positive. B is positive and its value is maximum. Okay. Now, how we find this? Let at instant A. This is instant A. This is your the axis of the instant 1. This is the axis of the resultant flux. Okay. This is the coil. So you can say apply the Maxwell-Corkscrew rule. So if this is the directions of the current, and definitely, or say if you fold if thumb is indicating the direction of the current, and then if you say fold your others rest of the fingers, so that this will show you the directions of the current, the magnetic flux. Okay, this is the magnetic flux directions, and see, this is the magnetic flux directions. Okay, but this is the current is entering here towards the way, and this is the current is coming out of the phase. So this is for and this is the resultant axis of the resultant. This is axis. Now for this this is for current the instant 2. This is for instant 2. Okay. So in this way, it will be observed that this resultant is rotating. Okay. Axis of the resultant is like this. It was the axis of the resultant. It was the axis of the resultant at instant 2, and this is the at instant 3 axis of the resultant. Okay, and you are finding the position of the resultant is changing every instant. Okay,